In this video, we're going to be talking about some of the basic solutions. We're going to go over the different components of a solution. We're going to go over some different types of solutions, how you can make things dissolve faster in a solution, and some of the math in a solution involving what we call concentration, and then what happens if you decide to add water to it. So a solution is just a homogeneous mixture. Remember, homogeneous. And a solution basically consists of two parts. The first part you have is the solute. That's the thing that you're trying to dissolve. And the solvent is what you're trying to dissolve it in. The general way to tell what is that the state of the solution will be about the same as the state of the solvent. Right, so for example, if we're talking about a saline solution, saline is sodium chloride, so just table salt, dissolved in water. Right, so the way that we know that water in this case is our solvent is because the solution will look the most like water. Right, so sodium chloride will dissolve in it. Right, so the solute's what you're trying to dissolve. So in this case, saline, sodium chloride is the solute, and water is the solvent. Right, so those are the two components of a solution. Now, whenever we say a solution is aqueous just means that it's dissolved in water, right? We've gone over this before, so it shouldn't be that much of a shock to you guys. All right, so things that affect the rate at which something dissolves. There are three primary factors that we can use to increase the rate of dissolving. And we'll use the analogy of, we'll say coffee, for example, because coffee is usually a good example of this. So most of you, when you order coffee, you decide to get sugar in it. What are some things that we can do to that sugar or to the solution in order to get that sugar to dissolve a little bit faster? Right, so first thing is temperature or heat. Sugar dissolves a lot faster in hot coffee than it does in iced coffee. Right, that's because in warm coffee, the solvent molecules in the coffee, the water, is moving a lot faster. Moving faster allows them to break up those sugar particles a lot more quickly, which means that it will dissolve a lot faster. Right, so heating it up is definitely one way to speed up dissolving. Another thing that we could do is stirring or agitating the solution, right? So you put your sugar in and you stir it with your spoon. What that does is that causes new solvent molecules to come into contact with the sugar, allowing it to dissolve a little bit more quickly than just having it sit there and having the sugar kind of disperse into the solution extremely slowly. And our third thing that we can do is we can crush the solute or powder it. Right, so if you think of it this way, if you take a sugar cube and you put it in coffee, it's going to dissolve extremely slowly because there's not a lot of surface area on a sugar cube. But if you crush it or you use granulated sugar, all those tiny little particles have all that surface area. And that means that the dissolving process or reaction can take place over that large surface area, which means it's going to be very, very quick. The next thing we should cover is concentration. Concentration is basically just a way of determining how much solute is dissolved in a solution at any given point in time. Right, and there are a bunch of different ways to do this. In fact, I'm just going to skip over most of these so you don't have to write a lot of these down. Right, so we won't do parts per million or billion. We won't do percent weight. We'll do percent weight if we're back later in the year, but for right now, we don't need it for what we're going to do later. Molarity is the one that we're going to focus on the most because molarity is actually the most useful one. Molality, again, if we get back later this year, we'll do a little bit with molality because molality has some very cool applications. And normality, again, we're not going to cover normality. We normally don't. But if you're going into a medical field, normality is going to be a very useful unit for you. Molarity is just moles per liter of solution. Right, so molarity equals moles divided by volume, but volume has to be in liters. Now notice one very important thing here. It's liters of the solution, not liters of solvent. Right? So oftentimes what you're going to see is if I want to make a liter of solution, I'm going to need less than a liter of water because the solute's going to take up some of that space. Right? So let's say I'm trying to make my sugar solution. If I want to make a liter of sugar solution, the volume taken up by the sugar is going to subtract from the volume of water I need to add. Right? So that's one important thing with molarity, is that it's dependent on the solution. Now right here where we have our equation, molarity is equal to moles over volume in liters, or the other way that we can write this is we can say that moles equals molarity times volume. Now if we're diluting, so if we're going to dilute a solution, diluting a solution just means that we're adding solvent. Then what we'll do is we'll use the equation M1V1 equals M2V2. This equation looks kind of familiar, right? It looks a lot like Boyle's law from our gas law unit. Again, the reason why this works is the number of moles that we put in at the beginning are equal to the number of moles that we put in at the end, right? Because if all we're doing is adding water, the amount of solute that we put in our solution hasn't changed. So the number of moles are still the same, right? We said that moles are equal to molarity times volume. So N1 is equal to M1 times V1, and then we have M2 times V2 on the other side, and we get our equivalent of Boyle's law. Right, these equations are actually fairly straightforward to use. We'll do a couple of examples with these, and then I'll set you guys off on your problem set. Right, so we have 3 practice problems here. Right, so if we look at the first one, we have 0.521 moles of sodium chloride dissolved to a volume of 250 milliliters. So all we have to do here is we try and figure out molarity. We know that molarity is equal to moles over volume in liters. The number of moles is 0.521. The volume is going to be 250 milliliters. 250 milliliters is 0.250 liters, so liters and moles. And this will give us, we just do our division, 2.08 moles per liter, or the other way that we tend to write this is 2.08 molar. Right? We use the capital M for molarity, and we call it a molar solution. Right? So either of these will be acceptable answers. This one, though, is the one that we typically use much more often. Right? Our second question, I have a volume, so I have my volume. I have my molarity. I'm being asked to solve for grams. Well, how do we get grams? I know that once I find moles, I can turn moles into grams. Right? So, again, we're going to say that molarity equals moles over volume. So if I plug in 2.00 moles per liter, that's our molarity, is equal to the number of moles that I don't know, over the volume, which 300 milliliters is 0.3 liters. Right, so what this gives me then, N equals 2 mole per liter times 0.3 liters, which is 0.6 moles, right? And this is moles of Na2CO3. So I have moles of sodium carbonate, but the question is asking me for grams. To go from moles to grams, I multiply by the molar mass. Right, so 1 mole of Na2CO3 has a molar mass of 106. Right, so moles will cancel out. So 0.6 times 106 gives us a final mass of 63.6 grams of sodium carbonate. right? So to make 300 mils of a 2 molar solution, I need to add about 64 grams of sodium carbonate to it, or washing soda. Right, this kind of calculation right here in a lab is actually the single most common solution calculation you'll have to do, which is how much solute do I need to make this solution? Our third question is a dilution question, right? Because you notice we have two volumes. So 50 milliliters is my V1, 12.1 molar is my M1, 428 mils is V2. I'm being asked to solve for concentration, so I'm being asked for M2. Right, so again, M1 V1 equals M2 V2. I'll plug these in. So I'm going to have 50 milliliters. Now again, just like the gas laws, it doesn't matter what unit of volume you're working with for this particular equation. Right, molarity equation in general needs to be in liters, but dilution equation works just like the gas laws do. As long as you're consistent on both sides, they'll just cancel out. Right, so 50 milliliters, 12.1 molar equals molarity 2 that we don't know, and volume 2 is 428 milliliters. Mils cancel out. So we're going to say that M2 is equal to 50 times 12.1 molar over 428, right? This is just our normal solution pattern. We multiply and divide, and we get a final answer of 1.41 molar. Now I hope this answer makes sense, because if we're adding water, the concentration, or the amount dissolved per unit volume, has to go down if we're adding water. So as volume increases, molarity decreases. Right, so that's it. That is the solutions video. You guys have a problem set that will be due next week, so please make sure you finish it by then.